Hi, the lecture for today is membership inference attacks. So this is a continuation of security and privacy issues against machine learning models. So this one is particularly focusing on privacy motivated attacks. And although there are other kinds of attacks that are motivated by privacy, the most prominent attack is membership inference. So that's going to be the central piece of the lecture for today. But as you will see, I will also touch up on other related attacks that are motivated by privacy or generally inferring some information about the data set or the model. So for the lecture today, what we're going to do is again, in the grand scheme of our trustworthy machine learning roadmap, we are now focusing more on the security aspect, the privacy aspect. And specifically, we're going to talk about when sensitive data is going to be leaked. So as you may know by now, privacy breaches or privacy has implications on safety. For example, if somebody's personally identifiable information, such as their address or other intimate details of people are disclosed through privacy motivated attacks, then this people could be targeted by other people who want to do harm to them. So privacy breach could entail safety implications as well. Okay, so that is sort of the context under which this privacy motivated attacks should be looked at in the sense of machine learning models. Okay, so specifically for the lecture, the first thing we're going to talk about is we'll broadly talk about risks in machine learning as far as privacy goes. So privacy risks in machine learning. And then we'll zoom in on one prominent risk called membership inference because it encapsulates different classes of attacks. It also enables doing other kinds of attacks if you do a good job of inferring whether a given input is part of a training set or not. Like I usually do for the other lectures, we're going to talk about why we should care about membership inference. And threat models that are out there and attacks, some representative set of attacks or attack strategies that are used for implementing membership inference attack. And then we'll close with some defense ideas that stand out as we speak. Okay, so as we may know, machine learning is everywhere. That's not breaking news anymore. But the fact that machine learning is pervasive has also opened this, possibilities of using machine learning for on privacy-sensitive data. And increasingly, machine learning is being used on privacy-sensitive data. So when we apply machine learning on sensitive data, there are risks that come with it, right? So, for example, in the medical domain, it is becoming very common that predictive models, are used for deciding different kinds of patient outcomes. For instance, diagnosis, for predicting different kinds of diseases or recommending treatment plans and so on. So the other important thing that we should know about privacy as it relates to machine learning or in general is this notion of, privacy regulations or privacy acts. For example, if you take the United States, for medical domains, there is this privacy act called HIPAA, where any healthcare provider or any actor in the healthcare system has to comply with HIPAA regulations to respect privacy of individuals, patients in the system. If you go to finance, we have a prevalent use of machine learning for things like credit scoring or deciding loans, loan approvals, doing fraud detection, fraud prediction, etc. And this is also subject to the right to Financial Privacy Act in the sense of the United States. And there are similar, acts or regulations in other countries or in other jurisdictions like the European Union, etc. Another example is education. So education is a place where a lot of privacy-sensitive data is stored about students, parents, and more. So education is one of the sectors that benefited from the boom in machine learning, especially on, for example, making learning platforms more adaptive and more customized and personalized. So when we do this, we want to make sure that we're not breaching or endangering privacy of individuals, specifically students who are consumers of the educational materials. So in the context of the United States, there is this regulation or act called FERPA, where if you're managing students' personally identifiable information, such as their personal details, their grades, and other things like counseling information, etc., that has to be compliant with the FERPA Act. Another critical example is criminal justice. And we have seen examples where machine learning is used for predictive policing, like deciding whether somebody is a criminal or not, or predicting, for example, locations in cities as to how hotspot they would be for example, for the next hotspot in a specific kind of crime or criminality prediction. Again, in theory, there's also acts that have to do with privacy when you, for example, arrest somebody or when you label somebody as a criminal, right? So, so as you can see, the common denominator for the examples I gave you here is that there is some need for compliance to privacy acts or privacy regulations. So privacy is interesting in the sense of machine learning, not only because it is technically possible to do privacy violations or attacks that would breach privacy of people, but if you do this, you would be held accountable because of the different kinds of regulations that we have in different sectors. Okay, so now with that background on how pervasive machine learning is on privacy-sensitive data, what are the risks that we anticipate when we apply machine learning in places like education or criminal justice or finance or healthcare? One of the most prominent attacks that could be mounted against machine learning that is trained on privacy-sensitive data is what we call membership inference. Okay. So roughly speaking, as I said, we're going to expand more on this throughout the lecture. So the central piece of the lecture is actually membership inference. But the idea is very simple. So given a model, F, and given an input X, when you do a prediction on the input X using the model F, the assumption here is that F is trained on privacy-sensitive data. So the adversary is asking one question, which is they want to determine whether or not this input X is used to train the model. If the answer is positive, if the answer is yes, then it's definitely a privacy breach because, as we said, the model was trained on privacy-sensitive data. The other kind of attack that we briefly talked about in the first lecture is what we call a model inversion. So model inversion is also a privacy-motivated attack because given an output, for example, the probability distribution of a label, and taking advantage or leveraging this output probability distributions, if you are able to infer sensitive information, let's say the face of a person that this is basically inverting or reverse engineering the process, which is given an output, you are going back and walking back and getting the inputs that led to that output. So this also has privacy implications. For example, in face recognition models, if you would be able to do this, and it has been done, this is a privacy breach. Another risk is training example extraction. So this is basically by simply interacting with the model, if an adversary can extract some number of training examples, let's say out of 1,000,000 training points, if you are able to extract, let's say, 1% or 2%, then depending on how sensitive that data is, the percentage could matter. But if it is privacy sensitive, it's going to be sensitive anyway. So even if you extract a small percentage of the training examples, that small percentage would translate to maybe a number of people, like 50 or 100 people as individuals. So privacy breach obviously translates to impacts on individuals. The other risk is what we call attribute inference. This is when looking at the output, pretty similar to the model inversion case, but in this case, the focus is more on inferring some sensitive attribute that was not even used to train the model, or that was not used as part of the training set. For example, by just looking at some output of a prediction coming from a model, if you can determine indirectly using the output of the model as a proxy, if you can infer the race of a person or the gender of a person or other intimate details of a person, then this is, again, privacy breach. And finally, we have model extraction. So our next lecture is on model extraction, but model extraction is the kind of attack that also fits into the framework of privacy risks against machine learning, simply because when the model that you trained is trained on privacy sensitive data, and somebody is interested in approximating or getting a copy or a near copy of the original model, that amounts to a privacy breach. So basically, you are stealing the whole model. The whole model becomes a privacy sensitive asset collectively after it is trained. That could also be considered as a privacy breach. But model extraction could also be treated in a broader term, in a broader context, where you look at model extraction as stealing, let's say, intellectual property or some, let's say, very sensitive details. For instance, if you train a model on national security secrets or whatever, right? But the bottom line is, based on some public data or some auxiliary data, if the adversary can locally train a model F prime that is functionally equivalent to the original target model F, then this could be considered as a serious threat to the original data set or the original model, depending on whether this is privacy sensitive or not. So that's sort of the highlight or a summary of what privacy risks we should be anticipating in machine learning. Okay, so as I said, we're going to spend more time on membership inference, but before we get there, I'll expand a little more on a couple of the privacy risks that I talked about. One of them is model inversion. So model inversion, as I said, is given an output of a model, for example, the confidence scores of the model for the different labels that it is predicting. The idea is to reconstruct a sensitive training data point, such as a person's face or a medical record, right? So this has been shown back in 2015 by this paper, the model inversion attacks that exploit confidence information and basic countermeasures. So to expand a little bit more on what they have done in this paper, what happened was they took face recognition or facial recognition model that basically returns the label and also the probability distribution of the different possible faces or labels or the class confidence. And using this class confidence score, they were able to reconstruct this approximation of the original face from the training data. And as you can see, this is pretty close. And if you know the person, you would basically recognize the reconstructed face as well, right? So that's sort of the danger or the real privacy risk that you see simply because the output that the model is returning by way of probability scores of the different labels is giving rise or is being exploited as a low-hanging fruit for crafting an attack that enables the adversary to recover the almost original training data point. Another related attack or risk is training data inference from large language models, and this has also been demonstrated quite recently. And what happens in this case is very interesting. So what the attackers do is they have a random input, so they prefix this random input with some, let's say, gibberish text. It doesn't have to even make sense. And this was demonstrated on GPT-2, but you know, the current versions of GPT 4 point something also suffer from similar problems, because there was a recent follow-up paper that also looked at this. And the problem, although it was not widespread as it was in GPT-2, because this was done in 2021, and the problem is still there. But the bottom line here is that you could go to the extent that you can trick the model to spit out like memorize data that it memorizes. For example, someone's contact information, like real contact information of a person. So as you can see, the output here is kind of redacted just for the sake of being ethical on the privacy of the person whose data is leaked here. Okay, so this is another example of privacy risks as far as extracting training data points from large language models. In attacks like this one, even if you are able to extract, let's say, one or two people's real contact information or other personal details, it's enough to say that there is privacy leakage, because you can attribute the leakage to one individual, and privacy, as you know, is measured. Privacy is measured better when you attribute the leakage to individuals instead of, let's say, the aggregate or average case privacy that we're used to measure. Okay, so that is just two more examples on the privacy risks that I covered in the previous slide. One more thing is, again, this is on training data extraction from diffusion models. So there's models that, given a prompt, a text prompt, they would produce, based on the prompt, they would produce images, right? And this kind of techniques, this kind of models also suffer from training data extraction. So the example you see over here is the caption was given as, the caption that is given here is living in the light with Anne Graham Lotz. And that was the original training point of training data. And what the extraction attack was able to recover was almost the same, except the face is a little blurred or a little denoised, but otherwise it looks pretty much the same kind of image. And they show in the paper a whole range of possibilities for different kinds of images with different color tones, etc. And also other things like logos of companies, etc. So this is a realistic threat in terms of privacy breach or intellectual property breach, because, for example, you're able to extract something that is copyrighted and all that, has implications at least on privacy, but it could also extend to situations like copyright infringement. Okay, so this is another recent example for where training data could be extracted from diffusion models. And as you can see, the extraction techniques are pretty precise, because what they cover is almost the same as the original training samples, with very minor visual differences. But that doesn't really matter, because if you know this person, you would know that this the one on the right is pretty much the same person. Okay, as I said, now let's zoom in on membership inference attacks. Okay, and the reason why we are going to zoom in on membership inference attacks is for the different privacy risks that I introduced earlier, membership inference attack could serve as either a precursor or as a foundation or a building block. Okay, so for that reason, membership inference attack is one of the widely studied attacks as it relates to privacy and machine learning. Okay, so what is membership inference attack? Suppose you have this training set, let's say the CFAR 10 data set, where you have 10 classes, the actual data set contains about 60,000 samples. So suppose you train a model using, let's say, stochastic gradient descent, and you end up with your model, a neural network, a deep neural network, typically a convolutional neural network, because this is an image data set. And you have a user who's gonna send out an input to this model. Let's say the user sends an input of a dog, and the model will predict this most of the time correctly. And in this case, dog is the output. Okay, so that's the standard or the typical use case. Now, replace this user with an adversary who is interested in answering this question. So take the same example of the dog as an input, and the adversary is asking whether this model, the CNN model you have here, is trained on this dog's image, right? So if the answer to this question is yes, then there is definitely privacy breach because the adversary learns something new. The adversary knows that this exact input was part of the training set. Of course, the CIFAR-10 dataset is a benchmark dataset that is not privacy sensitive, clearly. But if it is possible on CIFAR-10 or similar benchmark datasets, it must be possible on other really privacy sensitive datasets as well. So in summary, the goal of the adversary here is to inspect the model's predictions to determine whether or not sample was used to train. Okay, so positively answering this question, or at least with high confidence, has implications on privacy of the training data. So that's roughly the definition of membership inference at a high level. It's answering this question. But if I am a little bit formal on how we frame membership inference when we practically implement, is as follows. So a membership inference attack essentially is a statistical attack. So the kind of attack that you're doing is statistical. So you're estimating with some confidence, high confidence, that a sample is part of a training set or not. And membership inference attacks are not new, although the membership inference attack against machine learning models was introduced in 2016 or 17, right around that time. The idea of membership inference predates 2016 because in the medical domain, people looked at medical data and they generated like aggregate statistics from medical data. And looking at the aggregate statistics, people were doing this kind of attacks called tracing attacks, which is basically, given this aggregate statistics, can we trace back to an individual record or data point that was used to produce the aggregate record? The notion, the idea is pretty similar, except that now we're talking about the model. The model is our aggregate or distilled version of the data. Okay, so in that sense, it's a statistical attack, and it predates 2016. So the idea here is the adversary aims to infer whether some X, data point X, is part of the training set, D-train. And in this case, when candidate sample X is given, a model F trained on D-train, and the adversary's knowledge about the model and the training set could be designated with this symbol or notation K. So to capture what the adversary knows, because the threat model matters here. So the goal of a membership inference attack is to determine whether X is used to train F, assuming that the adversary knows something about the model, the data set, and other parameters. So more formally, you can put this as, for example, the attack function A, where A is parameterized by the input, the model, because we have to do the prediction on the input, and the knowledge of the adversary, and that this function A, the attack function A, would return 0 or 1, and 0 means the input X is not a part of the training set, and 1 means the input is part of the training set. Okay, so essentially what you're developing or crafting when you design a membership inference attack is a binary function, sometimes a binary classifier, as you will see it. And this binary function will say yes or no to indicate or to tell you whether the input was used to train the model or not. Okay, so that's a little bit of formalism into how you can frame the membership inference attack with respect to, let's say, the input X, the training set D train, and some assumption about what the adversary knows about data and the data set, the model, etc. Okay, so to this point, I didn't really tell you why we should care about membership inference, except that this is privacy breach, and that is a good enough reason in itself. But there are other reasons why membership inference is important and why we should care about it. One is, suppose you are a frequent visitor of a hospital, right? And you know that you're giving a lot of data points to the hospital, right? So you go through lab tests and you have hospital visits, you go to different specialists, etc. So there's a lot of footprint that you're going to leave as a patient there. So, and then all of a sudden you hear in the news that this hospital X is releasing a prediction API, a machine learning based prediction API that does, let's say, predictive diagnostics on some particular illness. And you would be naturally wondering, or you should be very curious as to whether the hospital has used your data to train the model. So you could be curious. And that curiosity, if the answer is yes, then you could sue the hospital because it's clearly a privacy breach. Another useful use case for membership inference attacks is membership inference attacks could be used for gathering intelligence for future attacks. So by simply deciding whether an input has been used to train a model or not, and doing this over time for a large corpus or population of inputs, you could essentially learn a lot about the behavior of the model, the distribution of data that you could reuse for launching more strong attacks or even other kinds of attacks. Another important reason is membership inference attack could be used as a building block for data extraction attacks. So the kind of attacks that I was showing you against diffusion models or large language models, etc., the central piece of those data training point extraction attacks are actually membership inference attacks. So the idea is, if given an input, if you have a high confidence that the input was used to train the model, then basically you got a copy of one of the inputs of the model, which over time, as you accumulate these inputs that have high membership inference score, then you would end up with a population of data points that come from the training set. So in that sense, it could serve as a building block for data extraction attacks. And more importantly, we can use membership inference attacks for good. So for something that benefits society. Suppose somebody comes and tells you, okay, here is a privacy preserving mechanism that I developed, and it's going to be a game changer, right? And there's a lot of companies and startups that would say, okay, we have this AI powered, technology that does X and Y, and among this is privacy preserving, let's say, predictions, right? So you might say, okay, wait a minute, I could try membership inference attack against this privacy preserving mechanisms, and I could effectively audit them and see whether they pass this test of membership inference. So as an auditing tool for checking whether the claim that is made by these products or services is really true or not, is a very useful and positive consequence of using membership inference attacks for good. Okay, so my hope here is that after I tell you these reasons, my hope is that you kind of broaden your anticipation as to why we have to look at membership inference attacks. Okay, now we know why we should care about membership inference attack. We know what it is. We know possibly the implications. Then the next natural question would be, okay, why is membership inference possible? What is really the root cause for membership inference? Okay, it turns out that, and this is not, again, breaking news, if you've worked with machine learning models, you already observed this phenomenon where the confidence of the model when the input is from the model's training data is oftentimes much greater than the confidence of the model when the input is not from the model's training data. Okay, so if you're an adversary who is carefully watching the difference between the model's confidence for some class of inputs as compared to other class of inputs, and you are putting these inputs in different buckets and keeping track of this confidence, you would eventually end up with two buckets where in one, the model is highly confident on average on a batch of inputs, and in the other, it is on average less confident. So given this phenomena called overfitting, where models are oftentimes more confident on the members of their training data, you could, safely, with high confidence, conclude that the ones where the model is more confident are mostly members. You may not get it 100%, but for the most part, you might get it right. Okay, so the low-hanging fruit in this situation is the statistical distinguishability of models' confidence on members versus non-members. So that statistical distinguishability is basically the key insight here. And also remember what we said about the nature of membership inference attacks. Membership inference attacks are essentially statistical attacks, right? And the statistical distinguishability helps out a lot here. And as I said, the root cause is this phenomena that we talked about in one of the previous lectures. This is called overfitting, where models are overall more confident on members of their training set than non-members, even when they're making the wrong predictions. Okay, so that's why membership inference attacks are possible. Okay, now before I go to specific kinds of attacks or representative membership inference attacks, let's spend some time on the threat model considerations, because every time we talk about an attack, we have to have a good handle on the threat model. Okay, so based on the information that is available to the adversary, we could broadly classify membership inference attacks into two. The first class and the most widely explored class of attacks is called probability-based. And here, what we are assuming is the adversary has access to some set of samples from the same distribution as the training data, okay? So if the training set was coming from, let's say, distribution D, the auxiliary data or some set of samples that the adversary has access to should also come from that, because if it comes from a different distribution, it's really hard to kind of compare the two. The adversary will have what we call oracle access to a prediction API with the label probability scores and the predictive label. Okay, so if there are 10 classes and the input was, for example, in the example of the dog input that I gave to the CFAR model, if it predicts dog, then it should also give me the prediction probabilities or confidence of the model on the other 9 classes, and that would make a vector of a probability of 10. And on probability-based attacks, the adversary might know model architecture. This may not always be there, but sometimes it is easy to fetch this information. For example, if a machine learning as a service provider would publish, let's say, a research paper where they don't tell you a whole lot as to the details of the model, but they could roughly sketch the model architecture for you, then it's fair game as an adversary to just pick that and take advantage of it when you design your membership inference attack. So that's the threat model when it is probability-based. The other case is the label-only membership inference attacks. So the information that the adversary has is just oracle access with only label. So not the probability, but just the label. So you give it an image of a dog, it would just say, this is a dog and nothing more. Okay, so in that sense, it's a more constrained kind of attack, and the information available to the adversary is not much. But the capability of the adversary is that the adversary can do, for example, data augmentation or perturbation of the target inputs to basically observe the model's sensitivity to these perturbations, because models would be insensitive to minor perturbations or minor data augmentation to members of their training data as compared to non-members. Because in real life, when we do training of models, we use these techniques. For example, data augmentation is a common practice for improving accuracy, low accuracy that comes that happens because of let's say data shortage or scarcity of data. So augmentation is one of the techniques that we use. So that what I talked about is on this part is focusing on the adversary. Okay, now a threat model wouldn't be complete if you don't cover the defender side as well. What are the assumptions and the capabilities? So for the defender, what we're assuming is the defender could be a machine learning as a service API, which exposes only predictions, not intermediate activations. For example, what is computed throughout the computation of the prediction. The other assumption is the adversary can't compute gradients through the model. So the adversary may not have that much intimate information about the model. The machine learning as a service API could be rate limited. For example, the adversary can't make more than, let's say, some number of queries per hour, per IP address or whatever. Okay. We know that adversaries could game this by, for example, doing IP spoofing and other countermeasures. But let's suppose, at least for the sake of this lecture, this works. And the adversary may not be able to perform more than, let's say, some amount of money worth of compute. So this is basically for limiting adversaries who want unlimited number of queries to use the target model as a labeling oracle to do extreme kinds of attacks, such as model extraction attacks. Okay, so these are sort of the threat model considerations for membership inference attacks from the attackers and the defenders' point of view. But every attack and defense that you're looking at is context sensitive. It depends on the data and depends on what you want, the resources available to you, etc. Therefore, you can take this description of threat models as sort of a general highlight, but maybe not like a complete set of rules. Okay, so that's on threat models. Now, what I'm going to do is I'm going to dive deep into some of the most representative attacks for doing membership inference. Okay, so the classic example of membership inference attack against machine learning models is this attack that was introduced by Chokri et al. Back in 2016. It's called the shadow model attack, because the central piece of the attack is what we call a shadow model, which we will discover what it is soon. So the goal of the shadow model attack is to train a model to infer whether or not a data point is in the training set of the target model. Notice the fact that we're training a model. So it's basically turning machine learning against itself, right? So our target is a machine learning model trained on privacy sensitive data. And the attack model that we're gonna train is also yet another machine learning model. Very funny, right? But this is a common practice in the space of, let's say, adversarial machine learning or privacy preserved machine learning. Okay, so what are the assumptions for this attack, especially as it relates to the threat model we just talked about? So the first thing is the attacker has access to a shadow data set, so some auxiliary data set that comes from the same distribution as the training set. This is very important, because if we don't get this right, the likelihood of the attack to succeed is pretty low. And the attacker has probability distributions of each prediction. So every time there is a prediction, the probability distributions of the classes would come out as well. And the attack unfolds in roughly 3 steps. The first step is where we do the training data collection to train our attack model. And that data collection relies on the shadow dataset. The second step is training the attack model itself based on the data that we collect. And the last step, obviously, is to run or execute the attack. Okay, so next, what I'm going to do is I'll expand on these 3 steps to give you a sense of how this could be done in practice. Okay, step 1, training data collection. So as we said, the assumption is the attacker has access to a shadow data set, D-shadow. So let's call it D-shadow. And this comes from the same distribution as the training data set, D-train. Okay, the training data set that the model was trained on. The goal is you're going to train shadow models on D-shadow to produce training data for the attack model A. So we're going to denote the attack model with A. And we're going to use the shadow data to train shadow models. So how do we do this? Here's how it's going to be done. So the first thing you do is you partition the shadow data set into, let's say, some number of pieces or some chunks, right? Subsets. So this could be done in many ways. I'm showing you the most simplified version of the shadow model attack, where I'm going to divide the shadow data set into 2 sets, this D in and D out. Okay, so as you can see, I'm using this subscripts in and out to mean for in, I mean the members, and for out, I mean the non-members. Now, after I do this, I'm going to choose a model architecture and train F shadow on D in to mean D in to mimic the samples that are within the training set. So the F shadow architecture, the model architecture, if the train model allows you the case where you would be having some information about the architecture of the target model, you can mimic that target model. For example, publicly available target model architecture. If not, you can also rely on a different model. You can take an educated guess. For example, if this is an image classification model that you're targeting to attack, chances are image classification models are trained on convolutional neural nets. And there is probably a state-of-the-art convolutional neural net architecture out there. So you can go grab that and tweak it a little bit and use it for training the shadow model, right? So it's not that hard to get something that is publicly available. Now, once you train F shadow on D in, what we're going to do is for each pair of input and labels, X is the input, Y is the label, in D in, you're going to do the following. You compute the prediction using F shadow of the individual inputs. So you're basically you're querying the F shadow that you trained on its own training set to populate the set of member datasets. And you're going to create the datasets, the part of the dataset for the attack model A that would qualify as in or members of the training set. And you're going to represent it as follows. So you're going to have a vector V, which is the probability vector. So this is the probability vector, okay? Probability distribution. Okay? And the Y here is the predicted label by F shadow of the input X. And the label that you're going to give it is in, because these are training examples of the shadow model F shadow. Okay? Now, so the probability distribution vector is going to be of size k, where k is the number of labels you have. For example, for CFAR 10, it's going to be 10. Okay, so you do this for each input in D. Again, you repeat the same process, but this time around for D out. So for each XY in D out, you're going to compute the prediction on F shadow again. And all these inputs that you compute prediction on will make the counterpart of the members of F shadow, because in D, you've never used the data points in D out to train the model F shadow. So by definition, every element, every data point in D out is a non-member of the training set of F shadow. And you would compose the feature vector for the non-members the same way. So V as the probability distribution vector, Y as the predicted label, and the label is going to be out, and everything else is the same. So that's how you would prepare the training data for your attack model. So basically you have, if for example, D in is 100 samples, and D out is also 100 samples, they don't have to be exactly the same, but oftentimes we do symmetric data set size just for the sake of fairness, not for the sake of fairness, rather for the sake of being rational on the probability of being a member or not. As long as you have this balanced set, when you compute membership score on average, it's better that you have the same number of samples from each side of the eye. Okay, so if there are 100 samples here, this will end up with 100 samples of feature vectors with labels, and the same way D out will also end up with 100 samples of feature vectors and the opposite label. Now you have a training set ready for training. So the second step is we're going to do attack model training, which is basically giving it the union of the members and non-members, and the important feature vectors are the probability distribution values, and you're going to train the attack model. When you train the attack model, as to the choice of the model architecture for the attack model, you can use the architecture of the target model itself, but that is not really important. Oftentimes, the attack model is a lightweight model because this is a binary classifier and the feature dimensionality is not that complicated. Therefore, you can, models like logistic regression or simple multi-layer perceptron could serve the purpose of training the attack model. So you have the attack model trained on this shadow data. And once you have that, now you can perform the attack. So basically you can take an input X, you query the target model with that input, you get the prediction vectors, the probability vector, and the predicted label, which makes the exact feature vector that you need for the attack model. You feed that to the attack model, and the attack model, as you know, is a binary classifier. It would say in or out, or it would say yes or no. So if it predicts in, the input is a member of the training set. If it predicts out, the opposite. It's not a member. Okay, so that basically is the end-to-end attack for a shadow model-based approach, where, as I said at the beginning of this attack, this is turning a machine learning model against itself by training an attack model, which is yet another machine learning. Okay, so that's one common approach to look at membership inference attacks. And since the shadow model attack was introduced over the years, the last 6-7 years, a lot of variations of this attack were proposed in the literature, and some of them, use just one shadow model. Some use a couple of shadow models compared to the original attack, which uses multiple shadow models. Okay, but the central piece or idea is pretty similar. Okay, now I will shift to different kinds of attack models where we don't train a machine learning model to do the attack model. We rather do this purely statistical based attacks because at the end of the day, membership inference is a statistical attack. So one of this non-shadow model based approaches is called prediction correctness based attack, which is very simple. But it might serve the purpose of membership inference. So the idea is when there is correct prediction, we assume that correct predictions are typical of member data points. So given an input, target model, you query it, you get an output. And if the output is a correct prediction, for example, it matches the ground truth label, we will say, okay, then this is a member of the training set, otherwise no. And the intuition behind this kind of simple attack, which doesn't require the complication of the shadow model training and all that, is because if a model is an overfit, so this model makes more mistakes on non-members than members. So that's the idea here. The other kind of attack is prediction loss-based attacks. So instead of checking whether the prediction is correct or not, we look at the loss that is incurred when a prediction is done. So yeah, the way this happens is you assign a score to a data point X using the target model's loss. So the score S could be computed as the loss, whatever your loss function is, of the prediction of the input using the model with respect to the true label that we have the model for the input. So this score can be now converted into a binary label like in or out or yes or no by using some thresholding mechanism. Okay. So for example, the thresholding mechanism could be, or the threshold could be estimated as the average or maximum loss of F on training data, which could be public information sometimes when the model owner reports, right? So basically, the way you can formalize this is given an input X, you would compute the score S, which is the loss of the prediction of the input with respect to the true value. And you have that Y. And if the score is less than some threshold, you would say yes. You would say this is in, otherwise out. And the intuition here is models are trained to minimize loss. That's what models do when we train, right? That's the bread and butter of stochastic gradient descent is minimizing loss. So if the loss is smaller, it is because the input is part of the training set. And sometimes models could achieve zero loss for members of their training data. So that's the insight or the intuition behind prediction loss-based attack. Another is prediction confidence-based attack. So instead of loss, we look at how confident the model is, and you would compute that score. And the confidence threshold can be chosen based on, let's say, the average or the minimum on the training data, if that data is available, or it could be determined from, let's say, a batch of predictions that you give to the model. So the idea is you would compute a score, which is a confidence of the model on predicting a given label on X. And when that score is, let's say, greater than some threshold, let's say the average confidence of the model, you would say, oh, this is part of the training set. Otherwise, it's not. And again, the intuition here is that models are, as we know, are more often more confident on training examples, even when they're making mistakes. It doesn't matter whether the prediction is right or wrong. Even when they make mistakes, they might be more confident. And we have seen this in even the funny examples of adversarial examples where the model has 88% confidence on an image of a tabby cat. And then when the model is given a perturbed version of the tabby cat and it predicts it as guacamole, it is almost 100% accurate. It's making a mistake, but it's more confident. So models could be more confident even when the predictions are wrong. Okay, so that is another non-shadow model-based attack, which you can very quickly do. And last attack that I'm going to describe here in this category is what we call prediction entropy-based attack. So the prediction entropy-based attack is basically computing the Shannon entropy of the prediction probability distributions over the K classes that you have for the model. And the threshold for this can be estimated as, for example, the average entropy of the model on training data, if this is available, or it can be estimated based on, let's say, attacker supplied batch of predictions. So you watch a number of predictions and you can compute the average entropy of the probability distributions of the confidences, and the Shannon entropy H of Y could be computed as, using the Shannon entropy formula. And you could use that. So as you know, entropy is used to measure how random an outcome is. So the less random it is, the more confident the model is, therefore it's a member, and vice versa. So again, the intuition that we're using here is models are more often more confident on training examples, even when they make mistakes on the predictions. Okay, so what I did in describing these attacks is basically I gave you two categories of attacks. Attacks which are learning based that require training an attack model, just like yet another machine learning model that attacks a target machine learning model. Or you can approach this with fast, more intuitive attacks that are based on some statistics and threshold, right? So these are the two broad classes of attacks that you will find out there. Okay, so enough with the attacks. Now let's talk about defenses against membership inference attack. Similar to defenses against poisoning and adversarial examples, there are several defenses that were proposed against membership inference attacks in the last 5-6 years. What I'm going to do, as I usually do, is I'm going to highlight the defenses that are working reasonably well as we speak. But this might change. Maybe 1 year down the line, we would find a better defense. But at least the ones that we have and that stand out today are going to be covered in this lecture. Okay, so as we speak, the most reasonable defense that we have against membership inference attack is based on this notion called differential privacy. So before I describe the exact way how this differential privacy notion is going to be used for making machine learning models resilient against membership inference attacks, I'll first give you an intuition as to what this differential privacy idea is. So the idea behind differential privacy is, and this is arguably the best definition that we have about privacy today, and you will see why. So differential privacy, the intuition is that suppose you've got two data sets, D1 and D2. Let's say this is D1. So let me call this D1 and let me call this D2. Okay. So in D1, I have, let's say I have my data points. Let's say my own record is in D1. So that's me. And in D2, it's exactly the same as D1, except that I just remove my record. Okay, so the difference between these two data sets is just one record, and that is my record. Okay, so what we're going to do in differential privacy is that for an adversary who is interacting with a mechanism or an algorithm that is answering queries or questions based on this data sets D1 or D2, we're going to make this algorithm randomized. So this is called a randomized mechanism, where by observing the answers to queries, the adversary won't be deciding whether the input or the output was computed based on D1 or D2. So if we can make sure that, and if we can, formally guarantee that whether the output was computed based on D1 or D2, what the adversary sees is exactly the same or more or less the same, and the adversary wouldn't make any inference as to where the output is coming from. That's essentially the idea. So D1 and D2 are in the literature of differential privacy are called neighboring datasets simply because they are the same except for one person's record. And the goal is the output of the mechanism M, when it gives out answer 1 or answer 2, doesn't enable the adversary to distinguish between the fact that the answer came from D1 or D2. And basically what we're saying is answer 1 and answer 2 or answer 2 is essentially the same, whether this person's record has been used as part of D1 or not. Okay, so that's sort of the guarantee that we want to offer a user who is contributing data to this data sets. So that was the intuition. So if you formalize this into a definition, because differential privacy is a definition, it's not an algorithm, it's a definition. And then you can instantiate this definition or use it wherever it makes sense. So the formal definition is as follows. So a randomized algorithm M provides what we call epsilon delta differential privacy if for any neighboring datasets D1 and D2, which means they differ only with one record, and all possible valid inputs as a subset of, the universe of valid inputs of the mechanism M, here is the constraint, okay? So the probability of the mechanism run on D1 producing something that is valid is less or equal to, or it's almost the same as, the probability of the mechanism run on D2 producing a valid result. And this, closeness of the outcomes is constrained by e to the power of epsilon plus delta. Okay, so what makes the mechanism randomized is the fact that we are doing the probability here. The distance between the two data sets is 1. These are neighboring data sets. The S here indicates any output in S, okay, any valid output in the universe of valid outputs from the mechanism M. The parameter epsilon is what we call the privacy budget. So it's basically the knob that we can tune to basically decide how hard it is to distinguish between D1 and D2. So the closer the two sides of this inequality are, which means the smaller the value of epsilon is, the better it is for confusing the adversary. And delta is what we call failure probability for the mechanism, because sometimes when you implement this privacy, differential privacy definition, some mechanisms could give you values that are completely useless because of the randomization, and we have to take into account that failure probability. So the natural question you may ask when I show you this definition of differential privacy is, how do we set this value epsilon? Because that seems to be a very important parameter here. And the same is true for delta. So in general, the rule of thumb for epsilon, or the privacy budget, is the smaller, the better. The closer the epsilon is to 0, the better. For delta, we want it to be much smaller, orders of magnitude smaller than epsilon. But the rule of thumb is that for a given data set, let's say the size of D1 or D2, because these two data sets are pretty close, except for one record, the value of delta should be set as, let's say, something less than 1 over the size of the data set that you're given. Okay, so that's the definition of differential privacy. And from the definition here, it's not automatically apparent as to how we're going to use this in machine learning. But, in a moment, I'll show you how this is going to be useful. So to kind of facilitate that application of this notion or definition in machine learning, let me give you a bit of an illustration here. So suppose you have a function f that was run on D1, and you got the true result, right? So this is a true result. So the randomized mechanism on D1 is going to be the true result plus some noise that would confuse the adversary, or that would conceal the true result. So for instance, if the function f that you run on D1 is a query that counts people who are 50 or older, right? So suppose this actually is a true query on the UCI adult dataset. So this is one of the, the classic data sets that are used in machine learning. So when you run the mechanism, the true count is 1792. And when you add noise, we would get something different from 1792, but not too far, from the true value, because at the end of the day, we want the output of the mechanism to be useful. For example, if somebody is doing statistical analysis based on this, we still want them to be able to do this while hiding the true value as well. When we are hiding the true value, we are basically making the mechanism that produces the value randomized. Okay. The question now is, how do we add noise, right? Because if we know how to add noise to this, we can also add noise to some of the things that we compute in the training, during the training. For example, we compute gradients, we could add some noise, but we should know how to do it. We should also understand how sensitive the functions are when we add noise. For example, in this case, we're counting. So the count is a function. The sensitivity of the count function is usually 1, because by adding or subtracting one record from a data set, the implication of that change on the dataset size is just one record on the count. So you're going to add noise, random noise to the query result. The key challenge here is how do we add noise to improve privacy, but this noise shouldn't also hurt the utility, right? So it becomes a trade-off between privacy and utility. So we have this noise mechanisms that we can use. One of the popular ones is called Laplace noise, and the other one is called Gaussian noise, based on Laplace and Gaussian distribution, respectively. So for Laplace noise, for instance, if you want to add a noise to a result of a function f on dataset D, you're going to randomly sample from Laplace distribution with the sensitivity S of the function that we're computing. For example, for count, the sensitivity is 1. And over here is the privacy budget epsilon. So this, the Laplace noise is a very handy approach, noise mechanism, when you have what we call epsilon differential privacy or pure differential privacy, where you don't need the delta. But in the Gaussian mechanism, you can incorporate delta. So this is again sampling from the Gaussian distribution with S as the sensitivity of the function, delta as the failure probability, and epsilon as the privacy. Okay, so at a high level, the way we are implementing or instantiating the definition of differential privacy is we will add noise to the value that we are computing. And this noise should be calibrated with respect to the sensitivity of the function that is computing the value, and also the privacy budget. So how do we do this for, let's say, stochastic gradient descent? If we wanted stochastic gradient descent to be privacy preserving or differentially private using the definition of differential privacy I just discussed, how do we do this? Okay, so what you see here looks cryptic and complicated, but as I go through it, you will realize that it is the same stochastic gradient descent that we know, but augmented with differential privacy wherever differential privacy makes sense. Okay, so basically what we're going to do is we're going to train our model. So the model here is theta. Theta is a vector of model parameters with the privacy budget, let's say epsilon budget, okay? So we have training examples, x1 to xn. So my training data set is has n samples. We have, let's say, a loss function L of theta, which is, one of the loss functions, such as the cross entropy loss that we compute on average on the training set. The parameters are learning rate, which we already know. The noise scale, because we need a scale for the noise, because we're gonna repeatedly visit our data set when we do stochastic gradient descent, because we are going to run this for multiple epochs. Therefore, we need some coefficient for multiplying, for doing the noise scale. Group size is basically the batch size that we use when we sample from the training set. And there is a bound for gradient node, because we're going to add noise to the gradient of the model, the loss function. And we're going to clip the gradients to make sure that the gradients with noise would not be abnormally standing out for some elements of the training set, because if that happens, then some of them might be standing out, and that could be an opportunity for privacy leakage. Okay, so the outer loop here is the number of epochs. For each epoch t and the total number of epochs you have, you take a random sample L of t at that epoch, so a batch with some sampling probability, in this case L over n. You compute the gradient, as we know. So for each item, for each data point in the batch, you're going to compute the gradient of the input xi as this, so the gradient of the loss for that particular version of the model at t, epoch t. And you're going to clip the gradient using the clipping bound C. And the reason why we do the clipping of the gradient is because we don't want some gradients to jump off the typical size because of the noise that we added, we will be adding. Once you have, so basically you don't have like a special outlier gradient. Now on the clipped gradient, you add noise. So you're gonna add noise, which is once you compute the average gradient, which is normally how we do gradient, you're gonna add the noise. So this is the noise part. And as you can see, this is from the Gaussian distribution, because Gaussian distribution is a normal distribution centered at 0 and with covariance this mean square. And C square, C is the clipping boundary. And after that, you just do gradient descent, which is theta t plus 1 equals theta t minus the learning rate multiplied with the clipped, the noisy gradient. So this one is the noisy gradient that you computed up here. Okay. And then you look at epsilon and delta and compute the privacy cost or leakage that you have observed so far. And when the privacy budget that you have set is reached, you can stop the training and say, okay, this is the best I can do under the circumstances or under the privacy budget I have. And that way you can make you can produce the final model that is differentially private. Okay, so one thing to note here is differential privacy is a very useful technique, and it's sort of the state of the art as far as defending membership inference attack and other attacks as well. But it comes with a cost. Differential privacy incurs some cost on the standard accuracy of the model. So it doesn't come for free. So you have to trade off, a reasonable amount of accuracy to gain this privacy guarantee. Okay, so that's how you can apply differential privacy as part of a stochastic gradient descent to make your training differentially private. And this is actually proposed by Google, people at Google in 2016, and it's now part of the TensorFlow privacy library. Okay, so that's how you can apply differential privacy by doing gradient perturbation or adding noise to gradients. So in this paper that we published in 2022, this is one of our papers, we looked at differential privacy across the machine learning pipeline. So you have the machine learning pipeline here, and we looked at what happens when we add a noise or do perturbation of the input before we train, and we perturb the objective function, in this case, the loss function. We perturb the gradient, which is similar to the DP-SGD setup I just discussed, or we perturb the model weights or the model parameters, or you perturb the predictions that are output. For example, you perturb the probability distributions without changing the label. And we run this against membership inference attack to see, where we stand as far as the different perturbation techniques or the different spots where we apply differential privacy. So I won't be spending a lot of time on this, but I will give you a highlight of what we observed. For example, when we compare input perturbation, gradient perturbation, and prediction perturbation, and compare privacy budget that we spend, the epsilon value, versus the privacy leakage, right? The privacy leakage, you would see that, for instance, the gradient perturbation is fairly low in terms of privacy leakage. Prediction perturbation, the same thing, but input perturbation incurs a lot of privacy leakage. So in this sense, for CIFAR 10 on a deep neural network, using input perturbation may not be useful because it has higher privacy leakage overall. We also looked at this for other datasets like COVID-19 and loan dataset and so on. Our observation is more or less similar. Okay, so this is an example of where how you can compare as a machine learning privacy practitioner if you are confronted with multiple choices of adding differentially private noise or using differential privacy across the pipeline in machine learning. This is one way you can evaluate. Another approach that uses differential privacy for a slightly different setup is this approach called pater, where we do what we call private aggregation of teacher ensembles. So given a sensitive data set, we're going to split this sensitive data set into, let's say, some number of disjoint data sets, disjoint subsets. And then we train on each subset what we call teacher models. And each teacher model is going to be predicting on a given input that comes from a public data. And the aggregated output is where we add the noise. So for example, when we do the majority vote of the teacher models on a given input from public data, so everything that is done with the teacher models is on private data. So everything to the left of this line is not accessible to the adversary. What the adversary has access to is this new student model, which is trained on the aggregated predictions of the teacher models on public data. And we will serve this as a prediction API, the student model as a prediction API, such that whatever it has distilled from the private aggregation of the teacher models ensemble would be used as a basis for making predictions on public queries. And that is the way that's done is you just do a vote count for each label, and you add Laplacian noise, for example, because this is a counting query, the sensitivity is 1, and you set some epsilon privacy budget, and then you add noise, and you would get the maximum out of this. And this would mask the true prediction, or at least change the distribution of the majority vote for the adversary not to infer this. Okay, so this is also one approach which falls into the category of prediction perturbation, but in a manner where you apply this using teacher ensembles. And one thing to note here is that for an individual who contributed a data set to this sensitive data set, the fact that we are splitting this sensitive data into disjoint subsets provides the guarantee that your data set, your data point would belong to only one of the subsets here. And recently, we also, this is one of our papers, recently we looked at this problem of defending membership inference attacks from a slightly different perspective. So not using differential privacy, but looking at this idea of preemptive exclusion of members. So the setup we have here begins pretty similar to the Pache approach that I showed you here, where we have a sensitive data set. We split this data set into n disjoint subsets, and then we use data augmentation to gain back on the signal that we lose by splitting the data sets. And we train this models in visual subsets, the augmented subsets, into individual models, F1 to Fn. And then when an input comes in, the first thing we do is we have an exclusion oracle that we have designed based on many ideas. The exclusion oracle will first decide whether the input is part of one of this model's training set or not. And if it finds that model, let's say f of I, among the n models here, it will exclude f of I and use the rest of the models as for the ensemble, or for, let's say, the majority vote that the ensemble is going to use. So the idea here is, if we do a decent job of precisely excluding the model that contains the input, we're basically canceling away the membership signal that comes because of the presence of that input, right? And also by definition, if you remove the input doesn't exist. Any attempt to do membership inference attack would be at best a false positive. So for that, we have a link to the paper here, but we look at the exclusion oracle from different perspectives. One is model confidence based, where we exclude the most confident model. The other is exact signature matching, where we given an input, we compare whether the input matches exactly one of the inputs in one of these models. If so, we remove that model. Because exact matching could be easily fooled with augmentation or perturbations, we also check approximate signature matching, where we do, for example, for images, you can use perceptual hashing techniques to search the neighborhood of a given hash value. And lastly, we also use this classifier-based exclusion, where we train a model to predict which model to exclude. So for all these techniques or oracles, we do a detailed evaluation. But to just give you a highlight of what this technique, we call it MIA shield, or membership inference attack shield. And we compared it against techniques like DP-SGD that I just described, and Pache also. and many others. So what you see on this plots is for different data sets, but if I just focus on CFAR10 because everything else is pretty similar. So the x-axis is the model accuracy, and the y-axis is the effectiveness of the attack measured as area under the curve of the attack. And 50% on aggregate for a membership inference, because we're computing the attack success rate on average, given the same number of members and non-members here. 50% is the same as random guess. So if it is 50%, basically the attack is not working. But as we know, attack effectiveness should always be looked against model accuracy or model utility. So utility versus privacy, right? So our technique is Mia Shield, which is the square, the green square. DP-SGD is the red cross over here, and the green triangle is space. So, and we have others like model stacking, memguard, and regularization techniques like MMT mix-up, which is a broad class of membership inference defenses that we compared against this. So I just want to focus on this blue circle, which is the undefended model's accuracy is, let's say, 70%, okay? Right, yeah, so 70%. Now, when we look at our technique, it's right here. So the attack's success rate is 50%, which means the attack is not working, but the utility of the model is not too far from the original utility of the model. But when you look at techniques, differential privacy-based techniques like DP-SGD and the Pate approach that I described, they are over here. So in terms of attack AUC, they are performing the same way as our approach. So our approach is as good as this differential privacy-based approaches. But look how far they are compared to the original accuracy of the model. So as I said earlier, differential privacy approaches, differential privacy incurs a lot. You have to pay accuracy to gain privacy. So in that sense, overall, on balance, our approach is much better because it is paralyzing the attack while also not costing a lot on the utility of the model. Okay, so the story holds for the other data sets as well, so I don't want to repeat myself here. Okay, so that's one of the contributions we've made in the space of defending membership inference attacks and how our technique compares against the state-of-the-art or existing approaches, including differential privacy-based methods and others. All right, so in this lecture, we started with machine learning being used, increasingly used on privacy-sensitive data. We talked about risks against machine learning models as far as privacy goes, and talked about membership inference, training data extraction, sensitive information reconstruction, attribute inference, etc. We talked about the trait models, specifically probability-based and label-only trait models of membership inference. We talked about specific attacks, representative attacks, namely the shadow model attack, where the attack is yet another machine learning model you train to attack a target model. And also a bunch of threshold-based techniques that are very quick to implement without the need for going through a lot of data or training a shadow model. And we talked about representative or reasonably well-performing techniques of defense, namely those based on differential privacy, such as differentially private stochastic gradient descent, or the Pate approach, the private aggregation of teacher ensembles, and also the Mia Shield approach that comes from our lab as well, which is one of the recent defenses that we published. So with that, we conclude the lecture on membership inference, and I'll see you for the next one.